oxymercuration followed by reduction. Another way to convert an alkene into an alcohol is by using the oxymercuration reduction reaction. For oxymercuration, we'll be using mercuric 2 acetate. Here is the structure for mercuric 2 acetate. This part right here is the acetate ion, and it can be represented as OAC. Or in short, you can write this as HgOAC twice. When one hexene is reacted with mercuric 2 acetate in the presence of water, followed by reduction with sodium borohydride, this is sodium borohydride, it's going to give us 2 alcohols, and these 2 alcohols are going to be in there as a racemic mixture. We will talk about the stereochemistry of this reaction later. Here again, Markovnikov's addition, Markovnikov's rule has been followed. The electrophile is going to be HgOAC. And between these 2 carbons, which of these carbons is going to get the electrophile? Now, which of these carbons has got more number of hydrogens? Obviously, it is this carbon, and therefore the HgOAC is going to get attached to this carbon. And water is going to act as a nucleophile, which needs to go on to the next carbon. The OH part is going to get added onto this carbon. And during this process, during this reaction, acetic acid is obtained as a side product. The mechanism for oxymercuration is pretty much similar to as what we have seen in the case of halohydrin and halogenation of an alkene. In the first step, mercuric 2 acetate is going to undergo dissociation, where a bond between the Hg and OAC and the acetate group is going to get broken to form the actual electrophile. Once the electrophile has been obtained, the nucleophilic attack of the alkene molecule onto the electrophile will lead to the formation of the cyclic mercurinium ion, similar to what we have seen in the case of halogenation. In the halogenation, we formed a cyclic halonium ion. So this does look pretty much similar to that we have seen there. So once the cyclic mercurinium ion is obtained, it will then be attacked by the nucleophile. Here water is the nucleophile, and remember this has to go in the position that's opposite to that of the cyclic 3-membered ring structure. So it will come in a direction that is opposite to that of the leaving group. So here is your leaving group. This HgOAC is going to leave from this carbon, right? And this nucleophile will always try to go and attack the carbon that is highly substituted. Between these 2 carbon, which one is highly substituted? This carbon is highly substituted because it has got greater number of R's. There is at least 1 R here, and therefore this is highly substituted. And a highly substituted transition state is going to be more stable, and therefore this nucleophile will go and attack this carbon, breaking open this ring. So this is going to be a protonated alcohol here. This part right here is going to be a protonated alcohol. This protonated alcohol is going to get deprotonated in the presence of the base, where the base comes and abstracts this hydrogen and neutralizes this positive charge. And in the last step, the CHgOAC bond is going to get converted into CH bond. This is basically reduction. So the bond between carbon and mercury is going to get reduced to CH, thereby giving us a final compound, which is an alcohol.